I'm Norman Wildberger, and today we're going to deal with the fourth and final of our main laws of trigonometry in hyperbolic geometry. After we've proven this cross law, we will have possession of four really important theorems in geometry, and we'll see that they're very powerful tools allowing us to do many interesting things. So the cross law is quite different in the hyperbolic setting as compared to the rational trigonometry setting in the Euclidean plane. But in fact, the difference is not quite as big as it might at first seem. Let's start by reviewing the cross law in ordinary Euclidean rational trigonometry. If we have a triangle like this with three quadrants, Q1, Q2, and Q3, and notice the capital quadrants alerting us to the fact that we're in rational trigonometry. We're in the affine setting, not in the projective setting of hyperbolic geometry. And corresponding spreads, S1 opposite, S2 opposite, S3 opposite. Here is the cross law in the Euclidean rational trigonometry. It's telling us that Q1 plus Q2 minus Q3 all squared is 4 times Q1 times Q2 times 1 minus S3. This is the rational analog of the cosine law. And in fact, there's three of them because we were looking at this spread S3 here, but we could just as well have written down a formula with S2 or S1. And why is it called the cross law? Well, because in rational trigonometry, the quantity 1 minus S3 is denoted C3, and that's called the cross between these two lines here. And an important observation here is that if we scale the triangle, the spreads don't change. In other words, if we dilated the triangle so that all of the quadrants would be multiplied by the same factor, say lambda, then this left-hand side would be multiplied by lambda squared. The right-hand side here would be multiplied also by lambda squared, and those two lambda squareds would cancel, resulting in the same value for S3, which is just a reflection of the well-known fact that similar triangles have the same angles, or in rational trigonometry, the same spreads. If you dilate a triangle, its basic shape doesn't change. The spreads at the three vertices haven't changed, even though the quadrants have been multiplied by a factor. All right, now let's have a look at the cross law in universal hyperbolic geometry. And it's the most complicated of the four main laws, but it's still very important. Right? So you need to remember this formula. What is it? Well, it's concerning a triangle with quadrants Q1, Q2, Q3. These are hyperbolic quadrants, and hyperbolic spreads between the lines, S1 here, S2 here, and S3 here. Capital S's for the spreads, small q's for the quadrants, to distinguish it between the Euclidean case. And the relation is Q1 times Q2 times S3 minus Q1 minus Q2 minus Q3 plus 2 all squared is 4 times 1 minus Q1 times 1 minus Q2 times 1 minus Q3. And what this formula does for us, well, it does many things, but one obvious thing that it does for us is it allows us to find a spread if we know the three quadrants. So if we know Q1 and Q2 and Q3, then obviously this is giving us a quadratic equation for S3, because the S3 is occurring only right there, and it's something squared equals something else. So there's going to be two solutions, or 0 solutions, depending on whether this thing is or is not a square. Now, in hyperbolic geometry, there's a duality that we've talked a lot about between points and lines and between quadrants and spread. So it will turn out that each of the four main laws of trigonometry also has a dual law. The spread law's dual is pretty well the same as the spread law, so that doesn't really give us something new. But the other three laws have duals which have new content. In particular, here is the dual of the cross law. We'll call it the cross-dual law. It's just obtained from this one by interchanging quadrances and spreads. It's also a valid law that applies to this triangle. So what is it? It's saying that S1 times S2 times Q3 minus S1 minus S2 minus S3 plus 2 all squared is 4 times 1 minus S1 times 1 minus S2 times 1 minus S3. And the presence of this dual law is very interesting because it's telling us that if we know the three spreads, S1, S2, and S3, then we can solve for Q3. At least we get a quadratic equation for the quadrants. So this is a very different situation from the Euclidean case. If you know the three spreads of a triangle, then you don't know what the three quadrants are, because you could multiply any one solution by factors, by scaling. Here, it's different. If you know what the three spreads are, then you can solve for the three quadrants, at least up to some quadratic equation. So there might be some solutions, or there might be two solutions. Somewhat reluctantly, I'm going to expose you very quickly to the corresponding laws of the cross law in classical hyperbolic geometry. Now, you don't have to understand these laws. I just want you to have a look at them, a very brief look. And actually, I want you to forget them almost as soon as we move on. Okay? I do not want you to remember these formulas. But in classical hyperbolic geometry, which is the geometry that you find in all of the textbooks on hyperbolic geometry, there is a hyperbolic cosine law. In fact, there are two of them, just like we have a cross law and a cross-dual law. So this is a law involving the three distances or lengths of a triangle, d1, d2, d3, and the three angles of the triangle, theta 1, theta 2, theta 3. Whatever those are, okay, whatever those are. Okay, and it's a formula involving hyperbolic trigonometric functions, cosh, sines, as well as the standard circular function, cosine or sine. And you see that there's a little bit of a similarity to what we were talking about. This formula here only has a single angle involved, so in principle you could calculate the angle if you knew the three distances. While this one only has a single distance involved and three angles, so in principle you could calculate a distance if you knew the three angles. But making any of these computations necessarily in practice involves a calculator, because you need to calculate inverse circular functions or inverse hyperbolic functions. And that invariably takes you outside of pure mathematics, because you are no longer able to get exact solutions. You have to work with decimal approximations. That's definitely not the case with our trigonometric laws, which only involve quadratic equations at the most. So we know exactly at all times where the solutions lie. Okay, so this is definitely a wrong kind of thinking. Okay, it's now, or it will be soon, hopefully, of historical interest mainly. So we are taking over from these and similar laws. All right, here's a good exercise to get you working with the cross law. There it is right there. I've rewritten it. And the exercise is to take that form of it and show that you can rewrite it in this form. In other words, that these two statements are completely equivalent. If you expand this all out and then rearrange the terms, you can put it into this form. Q1 plus Q2 minus Q3 minus Q1 Q2 S3 all squared equals 4 times Q1 times Q2 times 1 minus Q3 times 1 minus S3. Now the S3 occurs over here quadratically, but it also occurs over here linearly. This is a nice alternate form for a number of reasons. First of all, from it follows Pythagoras' theorem. That's an exercise that I gave you a few videos back. If S3 happens to equal 1, then this form of the cross law immediately tells us that this 1 will give us a factor of 0, so this right-hand side will be 0. And that means that what's inside the brackets here must be 0. And if S3 is equal to 1, then that's giving us the relation that Q3 equals Q1 plus Q2 minus Q1 times Q2. So exactly Pythagoras is coming out from that side when S3 is equal to 1. So the cross law inside it has Pythagoras' theorem as a special case. Another interesting observation is that the Euclidean cross law that we started the lecture with can be seen in this law as a kind of limiting case. So the limiting case when the three quadrances, Q1, Q2, and Q3, are very small. Okay, so this can happen if you have 3 points very close to the center of the circle. The three quadrances will all be negative, but they'll all be relatively small, like close to 0. So imagine that each of the quadrances is like 1 over 1,000, roughly. Then this product of Q1, Q2 is not just small, but it's very, very small. It'll be of the order of 1 over 1,000,000. And 1 over 1,000,000 compared to 1 over 1,000 is very small, so this is almost negligible. In fact, we can kind of disregard it. So the left-hand side is approximately Q1 plus Q2 minus Q3 all squared. And the right-hand side, well, if Q3 is very small, then this factor here, 1 minus Q3, is pretty well close to 1. And so the right-hand side looks a lot like 4Q1, Q2 times 1 minus S3. And that's exactly the Euclidean form of the cross law. That's kind of contained in there as a special or a limiting case when you have very small quadrances. All right, so now it's time to look at this important formula directly head on. Let's have a look at what exactly it says and let's try to prove it. So here's our official statement of the theorem. Suppose that A1, A2, and A3 are distinct points with quadrances Q1, the quadrants between A2 and A3, Q2, the quadrants between A1 and A3, and Q3, the quadrants between A1 and A2. And the spread S3 is the spread between A3A1 and A3A2. In other words, the spread made by the two lines passing through A3. Then this relation is satisfied between the three quadrances Q1, Q2, and Q3 and S3. And it's the same formula that I've been writing down already several times. So we want to prove that. Well, we're going to start out in the standard way. We start by introducing concrete coordinates for A1, A2, and A3. So we assume we have the three numbers that form the proportion of A1. We assume we have the three numbers forming the proportion involved in A2, and the three numbers forming the proportion for A3. Now, we've already established some formulas in this situation in the course of proving, well, the other three theorems. But in particular, the last video that we did, we proved the spread law. We proved a nice formula, and it was exactly this one here. It was related to this quantity I call the quadria of this triangle, and that was Q1 times Q2 times S3. This particular expression appeared, and I wrote down this formula here. So what is this? There's a minus sign first of all, and then there's a square on the numerator, and what's inside here? There's 6 terms alternating plus and minus. That's the determinant of the matrix that has rows x1, y1, z1, x2, y2, z2, and x3, y3, z3. So that's the natural determinant of a 3 by 3 matrix which is floating around here. In the denominator, the three relatively familiar terms. X1 squared plus y1 squared minus z1 squared times x2 squared plus y2 squared minus z2 squared times x3 squared plus y3 squared minus z3 squared. So we proved this relation between the 9 quantities and this particular product Q1, Q2 times S3. In fact, we also saw that it was equal to Q1, Q3 times S2, and it was equal to Q2 times Q3 times S1, where S1 and S2 are the other two spreads of the triangle. And in fact, the equality of these three things follows from the spread law, because S3 over Q3 is the same as S2 over Q2. And so you can substitute the S3 times Q2 with S2 times Q3. And similarly for this one here. Okay, so we're going to use this expression, but we're also going to use something else. We're going to use a remarkable and lovely formula that just drops down to us from the heavens. Here is this lovely formula. Okay, it's a polynomial identity. Left-hand side equals right-hand side. The left-hand side is this thing plus this thing plus this thing plus this thing minus this thing, the left-hand side, equals 2 times this times this times this. So the right-hand side is relatively short. The left-hand side is all of this. Let's have a good look at all the ingredients. So up here we have a minus sign, and then we have that determinant that we've seen several times now, squared. Okay. Plus the next term, here's this x1 squared plus y1 squared minus z1 squared term. And here, so to balance it, is x2 x3 plus y2 y3 minus z2 z3 all squared. This is like a dot product of a1 with itself. This is kind of like a dot product of a2 and a3, all squared. And then the next two terms are just like this one here, but with the indices rotated. So here's the x2 squared plus y2 squared minus z2 squared corresponding to this. And here now we're taking sort of a dot product of an a1 and a3, all squared. And the x3 squared plus y3 squared minus z3 squared times the dot product of the a1 and the a2, all squared. And then we have to still subtract the product of this thing times this thing times this thing. Okay, so if you have a rainy afternoon, what you can do is you can say, all right, I'm going to expand this all out. There may be dozens of terms, but I can expand that out because it's just something squared, so we can expand it all out, expand that out, everything all out, get some big bunch of all kinds of terms. And then we can expand out the right-hand side separately, and then we can compare the left-hand side term by term and see that everything matches up. Nothing left over on either side. Another way of doing that, which is more efficient, okay, is to look at particular terms. So for example, let's look at the right-hand side. And let's look at one particular term that might come up in the right-hand side. For example, this thing times this thing times this thing. That's going to end up being a constituent of the right-hand side. So that what is that exactly? That's 2 times, okay, there's an x2, x3, x1, x3, x1, x2. Well, all together, that's x1 squared times x2 squared times x3 squared. So x1 squared, x2 squared, x3 squared is occurring with a coefficient of 2 on the right-hand side. So you say, all right, let's look at that particular term and see where it will occur on the left-hand side. See if we also get a coefficient of 2. Okay, so let's look at this determinant squared. If we square that, can we get x1 squared, x2 squared, x3 squared? No, we can't, because each one of these terms has x's, y's, and z's in it. So that particular term will not occur in the square of the determinant. How about right here? Well, the only way to get such a term would be to take an x1 squared times x2 squared, x3 squared. In fact, that will occur. It will occur with a coefficient of 1. This times this thing squared, which is one of the ingredients when you square all this. So it's occurring once so far. How about up here? Well, same thing. We get it as x2 squared times this thing squared. That'll be another contribution of that same term. And then will appear also here x3 squared times x1, x2 all squared. So we're getting it once here, once here, once here for a total of 3. But there's another term we have to think about, minus this product. And in this product we see that x1 squared times x2 squared times x3 squared will occur exactly once. So 3 times from here, minus 1 times here. On the left-hand side, a total of 2 times. So we can tick in our mind that that particular term that we just talked about will occur equal number of times on both sides. And then you can argue, well, the whole thing is symmetrical, so there's no need to go through exactly the same argument for y2, for y1 squared, y2 squared, y3 squared. That's going to be exactly the same argument. But there are, of course, different kinds of terms that occur on both sides, and you have to go through each one of the different kinds of terms, making sure that the total coefficient on both sides is the same. So that would be a more efficient, more intelligent way of verifying this identity. An even more intelligent way is to get your computer. So I use Scientific Workplace, which is a program that allows me to write papers in LaTeX, which is a mathematical formatting language invented by Donald Knuth. And that's sort of the gold standard of mathematical typesetting. And Scientific Workplace does that for me, but it does a lot of other things too. In particular, it has a computational engine inside it. It's MuPad these days. And that allows me to, well, once I type this thing up, I can just type this equation up, and then I can press a button that says check equality. And it'll tell me whether these two things are equal or not. Say yes or no, true or not true. So that's essentially using the MuPad engine, which is an algebra computational package. There's also Maple and Mathematica, MATLAB. Those are all programs that are capable of sort of automatically checking identities like this. So the real test is just that you input them correctly. If you input them correctly, you can check with just a press of a button whether an identity like this is true. For a computer, this is not much different from checking some long arithmetical statement involving very big numbers. It just takes a fraction of a second to check it. Okay, so it's a remarkable identity. How are we going to use it? Well, we're going to square both sides of this identity, and then we're going to divide by this. Okay, so remember, this is a little bit like the final thing that we're going to get. It's something squared equals 4 times 1 minus q1, 1 minus q2, 1 minus q3. So I claim that this is almost immediately what you get when you do this to this identity. So if we square the left-hand side, well, we're going to get something squared. And when we divide by this, what are we going to get? Well, inside the brackets, when we divide this thing here by this times this times this without the squares, okay, we're getting the quadria. That's exactly the formula on the previous page. The formula was that the quadria was minus this squared divided by this times this times this. If we take this thing here and we divide by this times this times this, again without the squares, because inside the big square we're just really dividing by this times this times this, then the x1 squared and so on will cancel. So we're getting this dot product squared divided by this times this. And that's exactly the formula for 1 minus the corresponding quadrants. It's exactly 1 minus q1. So if you write down what q1 is, it's 1 minus this thing squared divided by this times this. So this thing squared divided by this times this is exactly 1 minus q1. And similarly, when you take this thing here and you divide it by that, you get 1 minus q2. And when you take this thing here and you divide it by it, you get 1 minus q1. And what about this? Well, this is exactly the same as what we're dividing by. So when we divide by it, we're just going to get minus 1. So it's all of that squared. And on the right-hand side, what do we get? Well, remember, now we're squaring this. So there's a 4 times this thing squared, times this thing squared, times this thing squared. And we're dividing that by this, times this, times this, with the squares. Well, that's the same as this thing squared times one of these and one of those, times this thing squared divided by one of those times one of those, times this squared times one of those times one of those. And those three terms, one with this numerator, one with this numerator, and one with this numerator, all squared, give us exactly these terms, 1 minus q1, 1 minus q2, 1 minus q3. Exactly the same things that were occurring over here. And now have a look at this left-hand side. This right-hand side is exactly what we want. This left-hand side, well, there's a 1 plus a 1 plus a 1 minus 1. That's plus 2. And here we have minus q1, minus q2, minus q3. And what was a? A was q1 times q2 times s3. So this is exactly the cross law, and we've proven it. It's a consequence of this identity together with a previous formula for the quadria. Okay, it's a tour de force, I admit. It's remarkable. I feel privileged to have, been involved in finding such a thing. But I really feel as if I haven't created this. It's just something I've accidentally discovered. Well, maybe not so accidentally, but it's just something that you find and you marvel at it, like finding a huge nugget in the outback or something. Okay, so a beautiful thing. So that's the proof of our fourth law, the cross law. We've done a fair amount of algebraic work. So if you've been able to follow this and you're still smiling, really good. That's really good. We are now in a position of considerable power. Considerable power. We can now do lots of things in this geometry fearlessly. So we've done a lot of work. Now we can reap the rewards, and we're going to prove a lot of interesting things. Let's start by having just one example today of a pleasant result that's a nice consequence of the cross law. This result is the equilateral triangle theorem, and it concerns an equilateral triangle in hyperbolic geometry. The statement is that if a triangle has three equal quadrances, and actually I'm obliged to say non-zero quadrances, so if a triangle has three equal non-zero quadrances, Q1 equals Q2 equals Q3 equals, say, Q, then it also has three equal spreads. S1 equals S2 equals S3 equals S. So there's then really only two numbers involved, this Q and this S. And furthermore, 1 minus S times Q all squared equals 4 times 1 minus S times 1 minus Q. So the first statement follows from the spread law. S1 over Q1 equals S2 over Q2 equals S3 over Q3. So if Q1 equals Q2 equals Q3, then S1 has to equal S2, has to equal S3. The exception being if Q1 and Q2 and Q3 are equal to 0. In that case, this wouldn't be telling us anything. So we exclude that possibility with our assumption. All right, so that's the first statement. So let's suppose that Q1 equals Q2 equals Q3 equals Q, and S1 equals S2 equals S3 equals S. So all three of the quadrances are Q, and all three of the spreads are S. Well, we can apply the cross law to the triangle. What's it going to say? The first term is Q1 times Q2 times S3, but all the quadrances are Q, all the spreads are S. So this is just Q squared times S. And then we have to subtract the 3 quadrances, but they're all equal, so we're just subtracting 3 times Q. Then we have to add 2 and square it. And we get 4 times the product of the 1 minus Q's. And there are 3 equal such products, so we're getting 4 times 1 minus Q all cubed. Alright, so that's a relation between Q and S, and you can expand it out. Just expand the cubic, expand the quadratic, get everything on one side, and then you can check that you get this relation after things simplify a little bit. S squared times Q squared minus 6SQ plus 4S plus 4Q minus 3 equals 0. That's what you get by simplifying the difference between the left and right hand side. And then this equals 0 can be rewritten in this way. 1 minus SQ squared equals 4 times 1 minus S times 1 minus Q. So the cross law implies this thing here. And exercise 28.2, you can check this. Just check that these things actually can be manipulated one to the other. Okay, a very good exercise for you to practice your algebraic skills. Remember, that's a very important skill to try to practice at as much as you can. Okay, let's have a look at a few additional exercises. The first exercise is a little bit open-ended, just to verify the cross law for a bunch of triangles whose quadrances and spreads you've already calculated. So during the course of the lectures, I've asked you to compute quadrances and spreads of particular triangles. For example, our standard triangle number 1. So somewhere, hopefully, you have a record of those quadrances and spreads, and you can make some computations to see if those quadrances and spreads actually do satisfy the cross law. Remember, there are 3 possibly different ones that you can choose. This is a kind of a little bit outside of what our usual familiarity here. So I'm going a little bit beyond here, and we're kind of seeing some things ahead of us here. But so what I'm asking you to do is to consider for a moment moving beyond the rational numbers. Okay, usually we work with the rational numbers. Everything that I say is usually for the rational numbers. But occasionally it's nice to have some extra numbers thrown in to make our arithmetic a little bit richer. In particular, to be able to solve quadratic equations that we can't solve over the rational numbers. So that's what I'm talking about here. So a field, the rational numbers, a joined square root of 2 and square root of 3. And what you should think about is simply this, perhaps a little bit naively, that you've got 2 symbols, root 2 and root 3, and they have the property that whenever you get root 2 and you square it, you get 2. And if you take a root 3 and you square it, you get 3. Okay, that's about all you really need to know. And then the question is to check that these 3 points, which don't exist over the rational numbers, okay, but over this bigger enlarged field, they exist, and that they actually define an equilateral triangle. So you can compute its quadrances and spreads. You can check that equilateral triangle theorem, and you can compute its quadri as well. And this question suggests a somewhat more serious question that maybe if you have a little bit more mathematical experience you can think about. The question is, are there any equilateral triangles over the rational numbers? So here's an example of an equilateral triangle, but I had to go outside the rational numbers to get it. The question is, can you find equilateral triangles just sticking inside rational numbers? It's an interesting kind of question. Alright, so well done. The last 5, 6 videos that we've done are very important. Okay, we've established the fundamental laws in hyperbolic geometry. And now we can apply them in a number of different directions. In our next video, we're going to look at right triangles. Triangles in which Pythagoras' theorem holds. But we'll see that there's other very nice things that work for right triangles. So we're going to talk about something called Thales' theorem, and we're going to talk about Napier's rules. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.